So this is Math466, Advanced Applied Analysis, lecture 5, I think. All right, so what I want to do is I want to start off with the proof of the Cauchy-Schwarz inequality. How many of you have seen the Cauchy-Schwarz inequality? How many of you could prove it? Okay, there's a lot of proofs of the Cauchy-Schwarz inequality. Okay, and so I will give you the proof by divine inspiration. So let's say f of g, then the integral of f g in absolute value is less than or equal to the integral of f squared to the 1/2 the integral of g squared to the 1/2. I'm being a little vague in terms of what space I'm integrating over. It could be minus infinity, infinity. It could be 0, 1. It could be multidimensional analog. Lots of different possibilities. Let's just say it's something real bad. Some subset of the real line could be the entire real line. So proof. The first thing whenever you prove something like this is you always want to look at, are there any special cases or assumptions or without loss of generality, things you can assume? The functions could be complex valued, but without loss of generality, I might as well assume they're non-negative. If they're complex valued, just replace f with absolute value of f and g with absolute value of g, and you won't see any difference. So without loss of generality, we can assume f and g are non-negative real valued functions. If not, just replace, as I said, each function with its absolute value. Okay? If you wanted to, what could you assume about the integral of f squared and the integral of g squared? What would it mean if the integral of f squared was 0? Yeah, basically f would have to be 0 almost everywhere. And so if f is 0 almost everywhere, then the integral of fg will be 0. So I might as well assume that the integrals on the right-hand side are not 0. If I wanted to, could I assume that these integrals are less than infinity?
Because if they are infinity, then you have that statement.
Yeah, it's really not that bad to show that a non-negative number is at most positive infinity, right? Because we've just shown that these integrals clearly, they can't be 0, because if they're 0, we're done. So you might as well assume that the integrals aren't infinite, because if they're infinite, there's nothing to prove. So again, it's sometimes nice when you're doing these real analysis proofs to just pause for a moment and think, what can I reduce it to? Where's the real action happening? And we're going to use the most important inequality in mathematics. So what's the best inequality? We've mentioned it before. It seems quite dinky.
X is less than x squared.
No, x is not always less than x squared. 1/2 is not less than...
If x is greater than 1.
So if x is greater than 1, x is less than x squared?
Yes.
No, because 1/2 is less than 1/4.
If x is greater than 1.
If x is greater than 1, then x is less than x squared. But that's not the most important inequality. It's close.
No, it's just non-negative.
Yeah, so if r is a non-negative real number, then r squared is greater than or equal to 0. Actually, do we have to say non-negative? If r is any real number, r squared is greater than or equal to 0. Right? So what we're going to do is we're going to study f minus lambda g in a product with f minus lambda g. What can you tell me about this? And we'll assume lambda is real. So I have a real function, real valued function. I multiply by the complex conjugate of a real valued function. Oh, well, that's just itself. So this is just the integral of f minus lambda g squared. What can you tell me about that integral? I'm sorry?
It's greater than 0.
Almost. You're very close.
Greater than
Greater than or equal to 0. So this is true for any lambda. So if you expand things out, what do we get? We get f in a product with f. Then we have a minus lambda gf. Then we have a minus f lambda g. Okay, so we get minus 2 lambda fg. And this is where it's important that I have things that are real valued. If they weren't real valued, f dot g is not the same as g dot f because we have to take complex conjugates. Since they're real valued, this is the same. I don't have to worry about taking the complex conjugate of lambda because lambda is real valued. So I'm crucially using realness here. This is why we made these simplifying assumptions in the beginning. And then we have plus lambda squared gg is greater than or equal to 0. Okay? I can choose any lambda I want. So I really should view this as a function of lambda for fixed f and g. What kind of function of lambda is this? It's a quadratic. Does it point up or does it point down? Points up. So we know it's got to look something like this. And so we could ask, what is the smallest this could be? How would we find the value of lambda where this is smallest? Okay, we could take the derivative. And then what? Find where the derivative is 0. And that gets the critical point, right? So smallest at the critical point. And we know that it's going to be a smallest, not a largest value. We know that this is a upward sloping. This is almost surely an apocryphal story, but I find it amusing. When they were building the stealth fighter and stealth bomber, the story goes that they forgot to check to see if they were maximizing or minimizing, and they just assumed something was a minimum, and it was actually a maximum. And if they had built it, this would be the "I'm here, I'm coming for you" plane. Okay? Probably a false example, probably just used to amuse students, but I like that idea. You always want to check and see max or min. Here we know that this g dot g, that's positive. Notice now how important it is that we've done some of the simplification before. Right? We know that g dot g is non-negative. In fact, we know that it's positive. We know that it's not infinite. This is a legitimate quadratic. All right, so when we take the derivative, we will get 2 g dot g lambda minus 2 fg equals 0. Therefore, the lambda that gives us the minimum value is just going to be, the 2's cancel, fg over gg. So that gives us the smallest value of this quadratic. All right. Now that we know what value of lambda gives us the smallest value of this quadratic, what should we look at? So we've got the point. What should we do with this point now? Yeah, let's plug it in. Let's see what that value is. So the smallest our quadratic will be is ff minus 2. Now we put in lambda. So we'll have fg over gg times fg. So we'll have fg squared over gg plus, now we have lambda squared, which will be fg squared over g dot g, and then we have a g dot g twice down here, so we'll have just a gg over here. And this is greater than or equal to 0. So we now get, oh, look at this. They're the same. So we get FF minus this expression minus FG over GG is greater than or equal to 0. So all we do now is bring this over and subtract, and we'll get FF GG is greater than or equal to FG. And that's what we wanted to show. Yes?
What happened to the square?
Oh, thank you. Yes, that should be a squared. Thank you. Yes. It would be very bad to drop the square. And so now, to get rid of the square, we take the square root of both sides. Thank you. And we get each of these to the 1/2. And that's what we wanted to show. So this is the long version of the proof. The short version of the proof, and if you look, I have some sketch notes. I say, on the board, Cauchy-Schwarz with lambda equals fg divided by gg. We can use this inequality for any choice of lambda, right? Is there a need to go through and motivate why we chose lambda? Can't I just write down what lambda is and say, consider the following inequality, and let's choose lambda to be f dot g over g dot g. We could do that. But then you have no idea of why was that lambda chosen. So this is the difference between following line by line and trying to see the big picture. How would you tackle something similar in the future? Where does that choice come from? It seems like a good natural thing to look at. You can also see now, since we have g dot g in the denominator, why I was quite concerned to make sure that g dot g is not 0 and it's not infinite. If it's 0, I'm in trouble. I can't divide by 0. If it's infinite, I'm taking lambda to be 0, and then this is just f dot f. So all of the assumptions, all of the restrictions we're doing over here is to make things nice later on. There's other ways you can prove the Cauchy-Schwarz inequality. At least this week, this is my favorite proof of it. It comes down to a nice parabola. We have to just find where's the parabola smallest. As was suggested, use calculus. And then just, since we now know that this holds for all values of lambda, let's put in the particularly smallest value, and it gives us something that's nice. The next thing you could ask is, when is the Cauchy-Schwarz inequality an equality? And if you look at this, when do you think you might have equality? Any thoughts on a relationship between f and g that might give you an equality? Yeah, if f and g are the same, it should be an equality, because then you have f squared to the 1/2, f squared to the 1/2. Okay, that's just f squared. What if g is equal to 5 times f? Then it would also be an equality. So with a little bit of work, as a nice exercise, you can prove that the only way you have equality is if f equals g almost everywhere. Or f is the same fixed multiple of g almost everywhere. That if they differ in any place, something's going to go wrong. And then maybe start looking at something like this. This is going to be the smallest value. If I take anything other than that value of lambda, it's going to be larger. So I'll let you think about how you might try to prove that the Cauchy-Schwarz is only an equality in that condition. Okay. So it's time now to do the prereqs we need to prove some of the big theorems in Fourier analysis. So the idea in Fourier analysis is you take a function and you replace it with a combination of sines and cosines or a combination of exponentials. And the big concern is, will that series converge? And if yes, will it converge to our function? And if yes, how quickly will it converge? And what do we mean by converge? Do we mean it converges pointwise, which is wonderful? Do we mean it converges such that the difference of their integrals is small? Or the difference of the square, the integral of the difference of their square is small? There's lots of different types of convergence. Not surprisingly, some are stronger than others. If you're converging pointwise, so then that means eventually you're going to be very close at every point. Then if you look at the integral of their difference on 0, 1, or their difference squared on 0, 1, that should also be small. But it's possible for the integrals to be small, but not to be close point-wise. Now, can they be far away from each other often? No, because then the integral of the difference will not be small. But it is possible to have the integral of the difference be small, but the function's not converging everywhere. And the hope is that the number of places where you don't converge is small. And the big idea is the smoother your function is, the more differentiable your function is, the better convergence you have. So I was preparing the lecture and I noticed that the book I'm using, which is my private notes, which has all the typos fixed, well, not all, some of the typos fixed, is not the same as the version you are using. That there's a big typo in the proof of one of the theorems in this chapter. And so if you've noticed this, email it to me. Whenever you notice mistakes, please email them to me. So what I want to do now is give us the preliminaries, the language, the functions we're going to need to prove convergence. The last thing before we start doing all the analysis is it's okay to discriminate so long as you don't discriminate by huge amounts. Mathematical discrimination is okay. When we build up the Fourier series, we like to treat all the Fourier coefficients as the same. It turns out that makes convergence a lot harder to work with. If we look at a slightly different series that's related, then it's much easier to show that that related series converges and converges well. This is similar if you've looked at anything with primes that you don't want to treat all the primes equally. You want to weight the prime by its logarithm. So a prime of around 100 gets a very different weight than a prime of around 10 to the 100. The weight will differ by a factor of 100. And then primes that are roughly the same size will be weighted the same. It turns out this makes a lot of the formulas nicer and easier to work with. So what I want to do now is what's called an approximation to the identity. How many of you have seen this concept, approximations to the identity? Okay, one person. What class?
I think we saw them in applied real, but also it's from the book.
Okay. Okay. So did anybody else see this in applied real? Okay. It's sometimes tough to remember what you've seen, and oh yeah, I think she might have said something about that, but I'm not quite sure. So the idea of an approximation to an identity is we have this idealized quantity called the Dirac delta functional. So if f is continuous at x equals a, then delta of f is f of a. And we write this as the integral from minus infinity to infinity, I'll put a subscript a over here, of f of x delta of x minus a dx equals f of a. So if you want to think about this, what would this mean? Basically, think of delta as a probability distribution. All of its mass is concentrated at the point x equals a. So if you're looking at the density is 0, 0, 0, jumps up to plus infinity, and then back to 0 instantaneously later. This is not a continuous function. Okay? You have a function that's 0 everywhere, but infinity at one point. How do we handle something like this? Well, we can take a step back and say we're defining an operator on the space of functions. So the operator is mapping functions to real numbers. And it's just assigning the value at a. It's the evaluation function. If you phrase it like that, this is not that surprising. So you just want me to evaluate f at a. Okay, I can do that. Let's think about why this might be the case. Let's look at an approximation to this. And so here's the point a. Here's a plus 1 over 2n. Here's a minus 1 over 2n. And let's say this is of size n over here. So if this is my function, if I now integrate from minus infinity to infinity, since my function over here is 0, before a to the 1 minus 2n and after a to the 1 minus 2n. All that matters is what's going on between these 2 points. So I would have the integral from a minus 1 over 2n to a plus 1 over 2n f of x times n dx. And the area under this rectangle is just going to be 1. So not drawn to scale, extremely large spike. Let's consider what this integral should be. So now what I can do is I can write f of x is f of a plus some function depending on the point a of x. Because the function is continuous, its value at x is its value at a plus a small little error. And this is going to tend to 0 as x gets closer and closer to a. So this would be equal to the integral from a minus 1 over 2n to a plus 1 over 2n of f of a plus c a of x dx. All right, so now we have 2 integrals. What's the integral of f? Oh, and there's an n dx, sorry. What's the integral of f of a n dx in this region? So what will the first piece give us? So what do I get when I integrate f of a times n dx from a minus 1 over 2n to a plus 1 over 2n? Not 1, close. I have f of a. I get f of a. I can pull out f of a. I can pull out n. I'm integrating the constant function 1 over an interval of length 1 over 2n minus 1 over 2n. Oh, that's an interval of length 1 over n. So because this interval is of size 1 over n and the height is n, I get just 1. So this piece is going to give us just f of a. And now we're left with the integral from a minus 1 over 2n to a plus 1 over 2n ca of x and dx. And now we just have to show that this integral is small. Well, since this is tending to 0, I can choose n so large that the difference between this and 0 is at most epsilon in absolute value. I have a large n over here, but the interval is of size 1 over n. So this over here in absolute value is less than or equal to the maximum of ca of x times n times 1 over n, and that goes to 0. So the idea is if I take this nice sequence of high spikes and I integrate my function against these high spikes, I just get back the value of the function at a. So what we're going to do is we're going to formalize this, and we're going to consider a class of functions to be an approximation to the identity if they converge to this and they converge in a nice way. And it turns out that there will be a lot of functions that we can do these integrals and get nice answers. So we say a sequence an is an approximation to the identity if the following conditions hold. I just want to put them in the same order. I think the first one we want is non-negative and integrates to 1. Okay, we just want non-negative. So we want an of x is greater than or equal to 0. We want the integral of an of x dx to equal 1. And then the last one, it depends a little bit on, are you doing it on the real line? Are you doing it on the interval 0, 1? That there's some special point that as long as you stay away from that, the integral is small. So here, if we do things about the 0, the integral over, say, x greater than or equal to delta of an of x dx goes to 0 as n goes to infinity. And here, delta is fixed. Okay? So you fix any delta and say, I want to be at least delta away from the point of action. Then no matter what that is, As long as you take n sufficiently large, you're basically saying there's negligible mass of an that far away. So in the limit, all of the mass is getting more and more concentrated near that point you care about. And so if you want, you can think of it as, a sequence. Oh, that's horrible. Think of it as a sequence that's getting more and more peaked. And if you just fix any delta, the mass outside, more than delta units away, is going to 0. Okay? So the first question is, do approximations to the identity exist? Well, here's an example. All right? So we at least have one family. This family is not continuous. Well, that's fortunately not a condition. I could have made this continuous by turning this into a triangle function. And if I do it into a triangle function, I've got to work a little bit more, but I could do something like that. Or I could have it drop off very sharp. There's a lot of things you could do. One of your homework problems, I think, is to show that if you have a non-negative sequence of functions, if you have a non-negative function which integrates to 1, you can actually create an approximation to the identity from that. Anybody know a really good function that integrates to 1 that's non-negative? When you see this, what function does this kind of make you think about?
Normal distribution.
Yeah, the normal distribution, the Gaussian, the bell curve. The bell curve is non-negative. If you put in the right normalization constant, it integrates to 1. So what you do is you take bell curves with smaller and smaller variance. Take a bell curve with variance 1/10th, 1/100th, 1,000th, 1,000,000th, 1,000,000,000th, 1,000,000,000,000th. It's going to be extremely concentrated at the origin. And so you have these wonderful sequences. Yes?
What does, so if A sub n is a sequence,
Right.
what does A sub n of x mean? Like,
Oh, this is the sequence of functions.
okay.
So an is a sequence of functions, and what I'm saying is these sequence of functions are the non-negative functions. And so what you would often do for if you have one function a, which is non-negative, let's say a of x is greater than or equal to 0. And let's say the integral of a of x dx equals 1. If I look at a n of x equals, I think, n a of nx, this is going to be non-negative, and it's going to integrate to 1. And because I put the n here, well, my function a has to decay because it integrates to something that's finite. It integrates to 1. So when I put the n here, this basically tells me that once x is as large as 1 over n, I'm evaluating this at 1. So let's say a is really small outside of, minus 5, 5. Once x is as large as 5 over n, we're now in the region where this is very, very small. So this is going to be a sequence of functions that are non-negative, that integrate to 1, and are becoming more and more concentrated at x equals 0. So this will give you a sequence that's an approximation to the identity. And I can't remember if I assigned this as a homework problem or not, but this is where they become very useful, is you take one function, and then you form a family from that. Okay, so why do we care about approximations to the identity? How are they useful in Fourier analysis? So let's consider again, En of x is e to the 2 pi I nx. We're going to let dn of x, this is the Dirichlet kernel, and we're going to define it to be the sum, little n goes from minus n to n, of e n of x. Okay? So this is a nice function. It turns out that this equals, and I have written it on the blackboard so I don't forget it, 2n, the sine of 2n plus 1 pi x divided by sine of pi x. Any thoughts what might be useful to prove this? We have a sum. What's really our favorite sum? I'm sorry? Geometric. Does this look like a geometric series? Is there a common ratio going from, say, E3x to E4x? Yeah, you multiply by e to the 2 pi ix. It's a geometric series. So basically, geometric series plus algebra proves this. Okay? The next is the Fejer. Oh, and this should be a capital N. The Fejer series, or the Fejer kernel. And this is defined to be the sum, n goes from 0 to n minus 1, dn of x. And when the dust settles here, you get sine squared of n pi x over n sine squared of pi of x. Why do we care about these? So Snf of x, this is the sum, n goes from minus n to n of f hat of n e to the 2 pi I n x. Right? This is the Fourier series that we want to study. It turns out that this Fourier series is just the integral from 0 to 1 of f of y Sn, oh, sorry, not Sn, dn of x minus y dy. So at least I think 3 of you should recognize what this is, because you've taken probability with me. It's a convolution. This is just f convolved with dn. And so instead of convolving with dn, what else could we study? What do you think might also be worth studying? Yeah, convolving with fn. So let's quickly show why this is the case. And then this will hopefully give you a motivation as to why we're doing all of this. So if we look at f convolved with dn, and this is evaluated at the point x. So the definition of the convolution of two functions is you just integrate f of y dn of x minus y dy. If you haven't seen convolutions before, it doesn't matter which one you define has the y and which one has the x minus y. We're assuming here that f is periodic. So we need f periodic. Let's see what we get. This is the integral from 0 to 1 of f of y. Now dn is going to be the sum, n goes from minus n to n, of e to the 2 pi I n x minus y dy. Right? Okay, so this is the same as the sum, n goes from minus n to n, the integral from 0 to 1 of f of y e to the negative 2 pi I n y dy, and then I have an e to the 2 pi I n x. That's just e n of x. But by definition, what is this quantity in here? That's just the Fourier coefficient at n. So this is just going to be the sum, n goes from minus n to n, of f hat of n e n x, and this is just Snf at x. So this gives you an idea of why it's good to convolve with the Dirichlet kernel. It gives you the Dirichlet series. Now the question is, just because I want to convolve with it doesn't mean I can necessarily convolve with it well. I have to then, what is this function dn? Well, fortunately, we actually have an explicit formula for what dn is. We have an explicit formula for fn. And it turns out that when you convolve with Fn, so you get the Fejer series Tn f of x, which is going to be f convolved with the Fejer kernel at x, and you get a sum, and goes from minus n to n, of n minus the absolute value of n over n, f hat of n, e n x. This is just algebra, right? All we have to do is a little bit of algebra to show that this is true. When little n is very small, this coefficient is basically 1. And it looks the same as the Fourier series. But as little n gets larger and larger and larger, the later Fourier coefficients get smaller and smaller weights. And this helps enormously with convergence. Right now, it doesn't look like this should make a huge deal. They're almost the same series. The only difference is I have this factor over here, which as little n gets larger and absolute value gets smaller. Big deal. All right. Let's look at the Dirichlet and Fejer kernels. So we have Dirichlet, we have Fejer. Do they both have a nice explicit formula? Yeah. So in that sense, they're both nice, that if I want to integrate against dn or integrate against fn, I can just use those nice explicit functions. Which do you think is better to integrate against, the Dirichlet or the Fejer? Which do you think has nicer properties for integrating? Neither one of them should have you jumping for joy. Oh boy, I get to integrate against ratios of sines. Thank you. Right? So in that sense, they're both bad.
The second one's easier.
Okay, why is the second one easier?
Because I think you can break sine squared into 1 minus cosine squared, and then you'd have 1 over sine squared, which is cosec squared. Which,
No, I mean, it's not bad to think about it, but they're both bad in that sense. What would be wonderful? What property would you like these things to have as n goes to infinity? We've got a sequence of functions. What would be nice? What would be a nice property for these sequence of functions to have? What would you like them to be? From earlier today. An approximation to the identity. Wouldn't it be nice if they're approximation to the identity? If they were an approximation to the identity, oh, well, then as n gets very, very large, integrating, that should just basically give me f of x. Oh, good, that means the Fourier series converges. Or if this is an approximation to the identity, the weighted Fourier series converges. If they're approximations to the identity, we have our convergence. So, we have two candidates on board, literally on board. Which one do you think is not an approximation to the identity? First or second? So you've got to be non-negative, you have to integrate to 1, and if you remove a small delta ball about the origin, the probability has to go to 0, the integral has to go to 0 as n goes to infinity. Which one of these do you think is bad, the Dirichlet or the Fejer?
The Fejer is definitely greater than, is definitely non-negative.
Okay, good. The Fejer is definitely non-negative. We've got squares and an n. Good. This is non-negative. What about sine over sine? Could that be negative? Well, let's look at the denominator. X goes from, say, minus a half to a half. Let's look at the interval minus a half to a half. And the reason is the action is happening at 0. I don't want to work with the round interval. So let's just go minus half to a half. What can you tell me about the denominator if I'm between minus a half and a half? It can be negative. And the numerator can be negative. So could they ever be of opposite sign? Well, the sign of 2n plus 1 pi x, it's highly oscillating. So if x is a small positive number, then this will be sine of a small positive number. The denominator will be positive. But as I move up a little bit over here, very quickly I'll get to a place where this is negative. So unfortunately, this function is highly oscillatory. You do not want to do highly oscillatory integrals. Think of this as a computational thing. If n is of size 10 to the 100, oh dear Lord, on the interval 0, 1, you're going to have like 10 to the 100 flips. You're going to have to know this function extremely accurately in terms of where you sample. Small differences, oh, terrible, absolutely terrible. So this is sometimes negative, that's bad. Does it integrate to 1 at least? So when you look at all these integrals, what's the integral of en of x? Cosine 2 pi nx plus I sine 2 pi nx. What are those integrals? Yes? No?
Well, isn't this sine term always going to be 0?
So the sine term is almost always going to be 0. There's only one time when the integral of the sine will not be 0. For which n? Because you have, here you have your cosine 2 pi n plus I sine 2 pi n. You just integrate term by term. What value of n is different from all others? So there's one value of n that's a different integral than all the others. 0. If n equals 0, you're just integrating the function 1, and you get 1. If you take any other value of n, you have cosine and sine for an integral number of periods. That's going to just be 0. So it at least integrates to 1. So, it's not an approximation to the identity, but it's not horrible. And it's at least highly oscillatory, so that, once x gets large, this is oscillating very, very fast. So maybe most of the action is happening near x equals 0. Okay? So the Dirichlet series, the Dirichlet kernel, it's not great, but it could be a lot worse. And that's why we can still get some nice results about convergence of Fourier series. Let's look at the Fejer series. It's clearly non-negative. Does it integrate to 1? Oh, there is a really, really bad typo. Sorry. There's supposed to be a 1 over n over there. So if you look at what's going on, each Dirichlet series integrates to 1. I go from 0 to n minus 1. I have n of them. I divide by n. So it will integrate to 1. So we've almost shown that the Fejer series over here is an approximation to an identity. There's only one property left. We have to show that if we stay away from the origin, if we move a fixed distance from the origin, it's going to be small. Okay? How would we do that? How would we see what's going on? We've got this expression. When is this expression easy to look at? When is it bad to look at? Where's the danger point in this expression? So we've got sine squared n pi x over n sine squared pi x. When you look at this expression, what's the danger value for x? 0. As long as x is not 0, when's the next time if x is plus or minus 1? Well, x is going to be between minus a half and a half. So as long as x stays away from 0, the denominator is fine. In fact, the denominator is going to be of size n. What about the numerator? How large is the numerator? So how large can the numerator be?
1.
Between 0 and 1, because it's a square. So the numerator is at most 1. So if you stay away from x equals 0, this expression looks like 1 over n. Oh, good. So if I integrate it, it's going to be small. The only problem is what's going on near 0. Well, if I look at what's going on near 0, I can Taylor expand things. The sine of u is u minus u cubed over 3 factorial plus u to the 5th over 5 factorial. So near x equals 0 looks like I have a 1 over n then this over here is going to look like, n pi x plus higher order terms. And down below, it's going to look like pi of x plus higher order terms. So then when I square things, the pi x's cancel, I'll have an n squared. So this is going to look like n. This is looking a lot like that approximation to the identity I showed you at the start of class. Something that's of size n in a very small window about the origin, and then decays rapidly elsewhere. So as long as x is small, we're going to be fine. And so now this is a question of just doing the calculations somewhat rigorously. What does it mean? How far can I take x to be? Well, if I fix x to be at least delta, then this will be at least sine squared pi delta. And as x gets larger than delta, this would even get larger. So if I wanted to make this thing as small as, if I want to see what's the worst possibility is when x equals delta. And so what you can do is just, so if the absolute value of x is greater than delta, then dn of x in absolute value is less than or equal to 1 over n sine squared pi delta. Remember, delta is fixed. Don't think of delta like 1 over n or 1 over n squared. Delta is fixed. Now you just crank up big N. And then you would have that the integral of this outside of this delta ball about the origin is going to be at most 1 over n sine squared pi delta. And so this proves that the Fejer series is an approximation to the identity. The Dirichlet series is not. Since it's an approximation to the identity, we should then have as a theorem that if we look at TNF, if we use this Fejer kernel, we should be able to get some kind of pointwise convergence. And then it's just a question of chasing down what assumptions do we need to make about our function. And so on Wednesday's class, we will actually do this and we will prove, so you should really read that section of the book to be familiar. There is a mistake in either the proof of Fejer's theorem or the proof of Dirichlet's theorem. Yes. Yeah, the author made a mistake. But this is why you always write a book with a co-author. There's the old joke that in Hardy and Littlewood, actually Littlewood never existed. Hardy just made him up in case any of the theorems turned out to be false. I will take responsibility for the error in the book. The error in the book is my fault. It has been corrected in my private PDF, so it's not too bad. But there is a mistake in the book, so find the mistake and email me the mistake in either the proof of the Fejer theorem or the proof of the Dirichlet theorem if you can before Wednesday's class. And then we will have some of the big convergence theorems coming into play.